Hey brother, I told you I'd make you a video of my machinery here. So I'm just going to do that, run through that process with you. Um, this is shot on my phone, and I don't normally shoot videos, so I apologize for the really low quality of this whole thing. But anyway, I'm going to flip the camera over to the other side, and then I got the machine right here, and then we can go through what all the parts are. So. Let me So here we have my DC power supply. We're going to start at something like 9 volts, 10 volts, 11 volts. Here, this is the microcontroller that switches the power. So we have DC power in. So these two guys here on the right are the input power. These are the switched power. So this can go pulse positive polarity and negative polarity. So this takes the DC and effectively just takes it and touches it this way, and then touches it this way, and then touches it this way. It's going back and forth. I set up these LEDs here when we first turn it on. They're going to run at low speed, and so you'll actually be able to see them bounce back and forth. You'll be able to see the signal. It's a pretty good little visualization. This is the Arduino board that I wrote some code so that it can take a signal from, oh, here's the machine. Here's the overall machine. This is the motor part, and this is the generator part. They're copies of the other. Each one is an identical copy of the other. Sadly, it's out of mild steel instead of silicon steel, so it's like pedaling in hummus as opposed to just on the street. So it's the hysteresis losses on mild steel are horrendous, but it works. So it's very, very poor efficiency, but I guess it's functional. This is I guess we can get you a close-up of the internals. So we have many different teeth here on the outside. This is a signal ring that runs, this is something called an optocouple. So it's an optical switch. There's basically two LEDs facing each other. And as the signal is interrupted by the teeth on this disc, the signal is then passed back to the Arduino, which passes it to the power controller, the H bridge, and then the H bridge will flip-flop the signal, the DC power, going to the motor. So it'll power the coils this way and then power the coils that way. And that allows, it's essentially a stepper motor. So you have here the teeth are in alignment, and so there's 16 teeth all the way around. So there's 2, 4, 6 in a triangle pattern. So these teeth are in alignment. These teeth are in alignment. Nope, I was wrong. These teeth are in alignment. They're behind this panel here. And so there's always 6 teeth that are coming into alignment and 6 teeth that are out of alignment. So that way you can have a essentially perpetual back and forth. And that way you only need to just reverse the polarity. Here on the magnets, these magnets are the sets. There's 6 magnets all the way around. Each of them are in opposition to each other. So this is a north pole facing that way. This is a north pole facing that way. And in the middle is the coil that switches which tooth that magnetic flux is going to go between. So all the magnetic flux is brought from this magnet through the coil, through that tooth, and back around when those guys are in alignment. And they are repelled from each other at the other signal. I'll have to probably break out a graphic to show you. If you look up the Flynn, Flynn, parallel path magnetic motor, you should still get some Google hits on it. You may have to dig for it, but there's a graphic there that will show you kind of what's going on, which is pretty cool. And the generator runs exactly like the motor, but I have an amp meter here to measure the current. And the current's pretty low, power's not very good, but it's very consistent, which is weird. It doesn't matter how many RPMs you run it. it'll pretty much always put out the same current, which is interesting. Probably has to do with the fact that I'm trying to do it out of mild steel. So anyway, yeah, that's it. Let's turn it on, see what happens. So here we have the DC power supply, run it to Arduino. I have a DC power cell. So that powers, the Arduino is now powered on. And there's our light for our switch. So if we give this guy a little bit of a tug, oops, we're missing something. Oh, there it is. Got to turn the power on. Oops, stand by. There we go. Had to reboot. So the camera, oh, you actually got some frame rate. That's kind of cool. So those lights are changing back and forth a lot faster than what you're seeing. You're getting a kind of a shutter interference pattern, so it looks like they're going a lot slower. They're actually traveling much faster. And so here we have the optical switch functioning, and they are shorted right now. So right now we're pulling about 0.2, 0.17 amps. And so if I turn the voltage wrong direction, there we go. I apologize for the sound. You see that it, if I go slower, it just dances around between 0.17, 0.15. It doesn't really go up much at all like you would expect. The normal generator would be producing significantly more current. It seems to be very RPM agnostic. So we're up at 17, 18 volts. So 0.15 amps. So let's take a voltage measurement. So here so this is dead loop, so this is dead shorted. I'm gonna take the short off so that we can measure, you can listen to it. So now it's doing no work. The generator circuit is now open, but if I close it and then put it in a dead short condition, it speeds up. Now, I'm going to make my Arduino print what the RPMs are. At some point, I have to program that in, but I'd really like to get the data on the RPM drop, but I have to open the switch so we can get a voltage reading. DC. So AC volts, 3.4 volts. But again, that doesn't really change by much. Even as you go down in RPM by a lot. That's probably half the RPM as what it was before, but we've only dropped half a volt. So, 4 volts, 4.1. So that's pretty good. That's definitely significantly less than, we're putting in 23 volts so we got 14 watts. So 14 watts, so 23 times 0.6. And so the motor's only consuming half of an amp, which is incredible to me. considering the load that it's driving. So we're only pulling 14 watts. And here, but we're only generating, what, maybe 1.4 watts, so a factor of 10 reduction. So that's definitely not anywhere close to over unity. On the other hand, we are using mild steel, so that's interesting. So anyway, we go and dead short it again. There it goes faster. And actually on a dead short, it's still able to measure. Let's see. No, that doesn't work. Yeah. So AC amps isn't much better. It's 0.23. I was measuring DC before. That's wrong. So it's measuring DC amps of 0.19, but that's incorrect data. So AC is 0.24. Well, that's not terrible, but it's still a tenth of what it should be producing. So anyway, there's my contraption. I'll close the video out. And I'll send this to you somehow. Maybe I'll upload it to YouTube. I'm not sure what. But anyway, talk to you later, man. Bye.